各位同学好，欢迎回到电磁理论的课程。Welcome back to the course of Electromagnetic Theory. In this set of slides, we will discuss about Chapter 3 of the textbook. In Chapter 3, we will attempt to derive wave equations and its solutions. So first, I will present the time harmonic form of the wave equations, and we will try to represent it as using the Phasor representation. And we can solve those wave equations in the so-called homogeneous materials. That is, the electromagnetic properties of the material can be represented with constants, and they are the same for wave propagating in different directions. Next, we will talk about the solution for those wave equations in homogeneous source-free media. And then after that, by applying the so-called boundary condition, we can derive the solution for the wave propagation everywhere. And the very last part of Chapter 3 is wave equation solution for in the cylindrical coordinates, which is also important when it comes to propagation of electromagnetic waves. Though it seems kind of theoretical, or it's actually have found its applications in different wave propagation related problems. 所以在本章中呢，我们会推导电磁波的波动方程式，然后找出它的一般解的形式哈。那比较特别的是，除了直角坐标系统里头的波动方程式解以外，我们也会看在柱坐标系统的解哈。那柱坐标系统的解在其实在看起来比较学理化啦哈，因为你会遇到什么Phasor方程什么的，但在实际的电磁传播问题的时候，柱坐标的解也还蛮重要的哈。Alright, so let's begin with the representation of electromagnetic fields. So the first one is the electrical field. As you can see in the small parentheses, you have dependence of position r, which is a vector, three-dimensional vector, and the dependence for time, t. And it's referred as the instantaneous form, instantaneous electrical field intensity representation, which means you will have to write up the time dependence as well as spatial dependence. So actually the instantaneous form is here. You can see that it can be separated as magnitude, which is dependent of position, and phase, phi, which is also a function of position, and the dependence of time. Note that here is a function, here is represented in the form of a sinusoidal function, cosine omega t plus phi. So we know that the signal is a continuous wave, single frequency continuous wave. This is the case for most of the wave propagation in wireless communications. Okay, so in wireless communication, more than 95% of the wireless communication signals are propagated in the form of continuous wave, except for the so-called ultra-wideband communication or spread spectrum communication, which use impulse to transmit the message. In general, for wireless communications, they falls into the group of narrowband. They use narrowband carrier frequency, and you applied modulation, so you can couple the information you would like to transmit into the continuous wave, which is a sinusoidal signal. All right. So in most cases, in general, the signal we are interested are of a specific frequency， 都是一个特定频率的。我们一般有兴趣的这一个电磁传播问题里头，一般都是一个特定频率的正弦波、连续波啦之间的连续波，那通常是以正弦波的形式，所以它会是一个 omega t， 会有一个 omega t 的这一个 dependence。So as a result, you know that so as I just explained, the wave that we are interested in most cases are of a single frequency, of a continuous signal of a specific frequency. So why bother writing the time dependence every time we will come to this kind of equations expression? So to make our life simpler, okay, so to make your life simpler, we can transform the so-called instantaneous representation into the phasor representation. So here's the phasor representation. Of course, you have to the left is the electrical field. As you can see, it's only a function of position. It only has the spatial dependence. And to the right, you have the magnitude part and you have the phase part. It's written as A exponential j phi. Where is the time dependence? You don't see time dependence in the phasor representation, right? Well, that's the tricky part of the phasor representation. It assumes the signal is a narrowband continuous wave. So it does have time dependence. It's exponential j omega t. But you know that, I know that, so let's agree that we know this, the so-called phasor representation has the time dependence as exponential j omega t. So we don't have to write it every time, okay? So the beauty of phasor representation is we don't write explicitly the time dependence. The exponential j omega t doesn't have to show in the phasor form. But every time when it comes to time derivative like this, you need to do time derivative. 你要在时间上去微分它的时候，你在时间上微分一个phasor讯号的时候，它就是调出一个 j omega 因为 exponential j omega t 去微分的话，它就有一个 j omega 嘛，每微分一次它就多一个 j omega. So every time you perform the time derivative, you get an additional j omega term in your phasor representation. So you don't see the t, but you have the result of the time derivative, time differentiation. Okay, so but so it's more convenient, more simpler to work out those electrical field, magnetic field in the phasor form. It's you don't have to write up all the exponential j omega t or cosine omega t terms. But if you want to present your final result, your final solution in the so-called instantaneous form, you need to perform this operation to transform phasor representation back to instantaneous representation. To do that, you will need to time the phasor representation with the exponential j omega t term and taking the real part of it. We know that exponential j omega t can be divided as equals to cosine omega t plus j sine omega t. and the real part is the cosine omega t. The real part of exponential j omega t is cosine omega t, like this. So after you perform the taking the real part of the phasor form with the product of exponential j omega t, you end up with the instantaneous form, like the equation at the bottom. Okay, so you only take the real part, then you can transform back to instantaneous form. All right, so be aware that in following slides, most of the derivation will be shown in the phasor form, which has no time dependence, but it does have time dependence. All right, it does have time dependence. So every time you perform time derivative, you end up with an additional j omega term. Okay, so let's go back to the Maxwell equation. So the top is the Faraday's law, the second is the Ampere's Kirchhoff law. As we already discussed last week, we introduced the so-called magnetic current and magnetic charge. All right, so in the Faraday's law, you have the left-hand side, you have the curve electrical field intensity. In the right-hand side, on top of the time derivative of magnetic field H, you have also an additional source, that is the magnetic current. So you have the minus of Mi minus j omega mu H. Note that this is the so-called phasor term, a phasor representation. So originally this should be the time derivative of B, the magnetic flux density. We replace B with mu times H, and the time derivative is replaced with j omega. Okay, so you have minus j omega mu times H. Again, for Maxwell equations representation, most likely the left-hand side will provide the spatial derivative. 好，所以在 Maxwell equation 里头，等号的左边都是空间的变化，所以这边我们看到是空间的梯度变化。The left-hand side is the spatial derivative, while the right-hand side you will have the source and time derivative, like this. You have the magnetic current and the time derivative of magnetic field. And the same thing can be performed on Ampere's Kirchhoff law. So again, the left-hand side is the curve of H, the curve of the magnetic field intensity, and the right-hand side is your source, the Ji, the impressed current, and the induced current. The induced current includes the conduction current, which is due to the conductivity in your material. So it's written as sigma E times E. Because of the presence of electrical field and the material's conductivity sigma E, you will when the electrical field applies on this material, you will induce a conduction current. And the Faraday's term is the so-called displacement current. Okay, so it's due what? It's due to the time derivative of electrical field, not due to the time rate of electrical field intensity change. So it's written as j omega epsilon prime E. Okay, note that the j omega terms suggest this is the result of a time derivative. Epsilon E means this is originally the electrical flux density D. Okay, and note that okay, let's remind you that here you have Mi and Ji. I stands for impressed current. So this is the current applied from the outside. Okay, so it's kind of the source. Okay, a forcing source to these equations. And the conduction current as well as the displacement current is kind of the result. Okay, so impressed current is the source, is the cause, and the conduction current, displacement current is the consequence. 所以前面这一个是讯号的来源啦，那后面是对应所发生的现象。你有外加的电流，你有外加的电场的话，你会产生传导电流跟位移电流。Okay? And the last two term can be collected as this: J omega epsilon E times electrical field intensity E. And now you can identify the epsilon E is the so-called effective permittivity. Effective 有等效的介电系数了等效的介电系数。Epsilon sub E is the effective permittivity. It has two terms. It should be divided into. It's a complex number. So it has the real part and the imaginary part. So it's written as epsilon prime minus J epsilon double prime. Okay, note that this minus sign. Okay, so when it comes to the complex number representation of effective permittivity, and the real part is the displacement current. So as you can see here, the epsilon prime is related to displacement current. The second part, the imaginary part, is related to conduction current. Can you tell me the difference between displacement current and the conduction current? Think about this. What is the difference between conduction current and the displacement current? Well, the displacement current is caused by varying electrical field. And you have the so-called electrical dipole moment. You have an electrical dipole. That is electrical, the positive charge and negative charge of the electrical dipole are rotating constantly within the material. They do not dissipate energy. Okay, it's driven by EM energy, but it doesn't cause energy dissipation. 换句话说，位移电流不会耗损能量。位移电流呈现的形式是在材料里头那些不断在转动的电偶极它们会正负不断转动，但正常的时候它不会耗损能量。Okay, so the displacement current does not dissipate electromagnetic energy. On the other hand, the conduction current, which generates real currents within the material, okay, driven by the conductivity of the material, do dissipate electromagnetic energy. So that's the reason why in the effective permittivity representation, one is the real part and the other is imaginary part. The imaginary part, which includes the conductivity of the material, represent the loss, represent the signal attenuation within that material. Okay, so be careful about the definition of effective permittivity. It can be separated into real part and imaginary part. The real part is actually the displacement current, and they do not dissipate EM energy, while the imaginary part, which is represented by the conduction current, does dissipate EM energy. Okay. Though in general, the permittivity and permeability are function of position, assuming that you have a non-homogeneous medium. But in the following derivation, and most likely we will encounter we're dealing with homogeneous material, so that the mu and epsilon can be written as constant within these equations. Okay, so the same thing can be applied to Faraday laws and Ampere-Circuitial law. And next we will try to do something interesting. We will use Ampere-Circuitial law and Faraday's law at the same time. We will substitute Ampere's law into Faraday laws and see what happens. So we begin with the top left corner. So here is the Faraday's law. The current of E equals to the minus of impressed magnetic current minus j omega times mu times the magnetic field intensity. First, we divide both sides with the permeability mu. To do that, you need to use the assumption that we are dealing with fields within a homogeneous medium, so that the permeability or the permittivity are constant. They are not function of positions. Okay? So we divide both sides with permeability. And then we take curl operation on both sides. Again, okay, we take curl operation on both sides. So everything curl operation are applied to every terms in this equation. And note that the j omega term here represents time derivative. Okay, so every time you come across j omega or omega, okay, yeah, because sometimes if you take j omega, if you take the time derivative twice, j omega to the square becomes minus omega to the square. OK， 好 ，j 平方等于什么？负1嘛，所以只要你有2次的时间偏微分的话，你的 j 欧米伽的平方就会变成是负的欧米伽平方。Alright, so after doing this, after taking the curve on both sides on everything, you found that the very last term is the curve of H, so that you can substitute the Ampere-Circuitial law like this into this term. So you replace curve of H with impressed electrical current J and the induced current due to permittivity epsilon E. So after doing this, you have minus j omega ji and omega to the square epsilon E. Okay, so this is actually the time derivative once. Perform the time derivative once. This is the result of perform time derivative twice. Okay. So now we have electrical field intensity, magnetic currents, electrical currents. So let's try to reorganize, massage this equation a little bit. We try to put the source and result on different sides. So on the right hand side, you put the source. You have magnetic impressed current, you have electric impressed currents. The magnetic impressed current is in the form of curl operation. So you know that the spatial difference, the difference in spatial distribution of magnetic current is the source for electrical field in the space. Also, you have the term j omega j. The current also can be, the impressed current J also can be the source for electrical field intensity. However, the production of electrical field intensity is through time derivative of J. You know the j omega term. So that means as long as there are time difference in the amount of impressed current, it will induce electrical field intensity E. And on the left hand side, you see that the first term is the curve of E. So you take the spatial derivative of E twice. So that is the second order differential equation of E. Also, the second term goes like this: omega to the square times epsilon times E. So, as I remind you earlier, when it comes to omega to the square, it means that you have performed time derivative twice. So on the left-hand side, you have second-order spatial derivative, and you also have the second-order differential equation in time. So equations present in this form is referred as the second-order differential equation of E, and this form is particularly important because it represents the so-called wave equation. 好，波动方程式。波动方程式里头，它必须要有空间的二次偏微分以及时间的同时有空间的二次偏微分跟时间的二次偏微分项，而且它们是分开来的。我要在直角坐标系统了哦，之后我们看到柱坐标系统的时候，或者球坐标系统的时候，它其实有一些 couple 的项，但在直角坐标系统的话，它是分开的，干干净净的。OK。So this is the result for electrical field. We can do the same thing on on Ampere Circuitial law. We apply the Faraday's law equation into Ampere Circuitial law. So we begin with the Ampere Circuitial law from the top. Here is the curl of H equals to impressed current and displacement current, induced current. Okay, so you divide both sides with epsilon E, the effective permittivity. So, and then you take curl operation on both sides. So on the left hand side, you have the curl of H, and on the right hand side, you have the curl of J, which means it is taking effect by taking the spatial derivative of electrical current. And the very last term is J omega times curl of E. And as you can see here, the curl of E can be substituted with representation from Faraday's law. That is, you can replace curl of E with magnetic impressed current and induced currents due to time derivative of magnetic field intensity H. So by substituting curl of E into this term, you have minus j omega mi plus omega to the square mu h. So you know this is the first one time time derivative. This is the second order time derivative because you have the omega to the square term. And again, we put source and result on different sides. So on the left hand side, you have the field distribution. The first term emphasizes the spatial difference. So you have a curl of H. That's a second order spatial differentiation. The second term emphasizes the time variation. You have the second order time derivative. So you begin with the omega to the square times mu times H. And on the right hand side, you have the source. The source can be electrical current, so because you see Ji, and it can also be magnetic current. However, the magnetic current and the electrical current take effect in different ways. For electrical current, the effect is so the magnetic field distribution. For electrical current, the effect takes place by finding its spatial differentiation, by finding its spatial variation, 空间上面的变化. For magnetic current, the effect it takes effect by looking into its time difference. So you see the j omega term. The time domain difference of magnetic current shall produce magnetic field. Okay? So next, we can look at the two equations at the same time. So let's look at the two equations jointly. So you can see they are in a relatively symmetric format. Again, for equation 1, we multiply both sides with mu, and for equation 2, we multiply both sides with epsilon e, so that the first term begins as the curl of E and the curl of H. The second terms will have the similar dependence of omega to the square times mu times effective permittivity epsilon E. Because of this result, we can replace minus omega to the square times mu times epsilon with the so-called propagation constant, 传播常数 propagation constant, gamma to the square. Okay, so we replace the constant of the second term on the left-hand side with gamma to the square. And again, I'd like to remind you that the second term represents the time difference, time domain variation. The first term is spatial domain variation. The second term is time domain variation. On the right-hand side is the source. You have magnetic impressed current, you have electrical impressed current, and in the two equations, they work kind of differently. In the first equation, when it comes to electrical field, the source for the production of electrical field is the spatial variation in magnetic current and time domain variation in electrical current. And on the other hand, for magnetic field, the magnetic field is produced by spatial variation in electrical current and time domain variation in magnetic current. Okay? Now, let's go back to the propagation constant. Okay, so let me spend a few seconds to discuss the propagation constant gamma. And as you can see, it has omega to the square, which is the result of time differentiation, and the material property mu and epsilon. In general, mu the permittivity and epsilon mu the permeability 介词系数 and epsilon the permittivity 介电系数 are complex numbers. They are complex numbers. And the product of the two complex number times omega to the square, taking a minus sign over here and taking the square root of that, would you end up with a real number or a pure imaginary number? Well, I bet most likely it will end up with a complex number. So let's say the propagation constant is a complex number which appears in the form of alpha plus j beta. Okay, so alpha is the real power of gamma. It's referred as the attenuation constant, and it actually represents the dissipation, the attenuation of electromagnetic energy within the material. While the second term, the j beta term, which is imaginary term, is referred as the phase constant. Okay, so it represents the phase variation of the signal of the field, and they do not provide signal attenuation. They do not provide power dissipation. Okay, so the real part is related to power dissipation. The second part, the imaginary part, is related to signal variation in the angle in the time domain. Okay. All right. So with the substitution of propagation constant gamma, the two equations can be rewritten like this, where gamma is actually a complex number represented with alpha plus j beta. and they are actually the square root of minus omega to the square times mu times epsilon sub 0. Now, let's substitute the complex permeability and complex permittivity into the representation of propagation constant. So we substitute mu with mu prime minus j mu double prime, and epsilon e with epsilon prime with minus j sigma e over omega. So let's review this definition again. So which part is related to attenuation, is related to power dissipation? This part. Okay? So the imaginary part of the permittivity is related to power dissipation because it contains the conductivity of the material. So it generates real current, real conduction current. So it provides power attenuation, power dissipation. On the other hand, the epsilon prime, the real part of epsilon, stands for the displacement current, which means the rotation of the electrical dipole moment. So they do not provide signal attenuation. So by comparing the representation of permittivity and permeability, you can have a general idea that the second part stands for attenuation in magnetic material, while the first part stands for phase variation, the magnetic dipole moment rotation within the magnetic material. Okay, in most cases, in most of the material that you shall encounter, the mu is simply a real number of mu prime. Okay. Alright, if you do the product of mu with epsilon e, you end up with 4 terms. And because they are all complex numbers, so the product of the 2 complex numbers end up with 4 terms. 2 of them are real and 2 of them are imaginary. So you should do this yourself, but this equation kind of summarizes the result. Okay, so first is the imaginary part, the second is the real part. Okay, it's kind of I admit that this looks kind of scary, kind of complicated, but let's see. So let's assume that the material is lossless, which means the permittivity is a real number, the permeability is also a real number. So the conductivity within the material sigma e equals to 0, and the mu double prime term equals to 0 as well. Then the square of the propagation constant gamma can be greatly simplified because sigma e goes to 0, mu double prime goes to 0, so these 3 terms all goes to 0. You end up with the only term is minus omega to the square times mu prime times epsilon prime. They are not related to attenuation. Okay, so as you can see here, for the lossless case, because the imaginary part of epsilon and mu are both 0, so the gamma, the propagation constant, end up with as a pure imaginary number equals to j beta, and beta equals to omega times the square root of mu prime times epsilon prime. So the propagation constant is purely imaginary. In that case, there's no attenuation. Okay, the alpha, the attenuation constant equals to 0. So for lossless case, gamma to the square equals to minus of beta to the square. Okay, so this is for lossless medium, such as free space, okay, or low loss material. Alright, let's go back to the 2 equations we have derived in the previous slides. Here is the curvature of E plus gamma to the square times E equals to the source, you have the spatial variation of Mi and time variation of Ji. Now we will introduce new tools, new technique. That is the vector identity. And this is, when it comes to vector identity, it's valid for any vector, for any scalar. So the left-hand side is the curve of a vector A. Again, this is valid for any vector. 任何的向量都遵守我们这边所写出来的 vector identity. Okay? So curve of A equals to the gradient of the divergence of A. Okay? The gradient of the divergence of A minus the Laplacian of A. As you can see, they are both second order spatial derivative. 二次的空间偏微分，只是它用的操作不太一样。所以前面第一项是先取散度，再取梯度，后面是取 Laplacian。后面是取 Laplacian。So by substituting the curve E with the gradient of the divergence of A minus the Laplacian of A, the original equation becomes this. Okay. So the first two terms are still the spatial variation. Okay. The second term is time domain variation. Now let's identify. Okay, now, well, we will use the, so far we have just used the Faraday's laws and Persecution law, and as you know, Maxwell equation have 4 equations, so we will attempt to use the last 2 equations. So here we will use the Gauss's law of electrical field. Gauss's law of electrical field. It states that the divergence of electrical flux density D equals to the electrical charge density at that point, low EV. Okay, so the divergence of E within the first term can be substituted with divergence of D divided by epsilon. Okay, so we use these terms here. As a result, as you can identify here that electrical charge density is actually the source, not the result, not the effect. Electrical charge density is the source. So source should be placed in the right hand side. So now we can move the second part, the divergence of E, as the result of gradient of low into the right hand side. Okay, so the left hand side is the Laplacian of E and the second order time derivative of E. On the right hand side, you have spatial variation of magnetic current, variation of electrical current, and spatial variation of electrical charge. So spatial variation of electric charge is also a source for electrical field, and the spatial variation of charge appears in the form of gradient, 梯度的形式，用梯度的形式出现。So if we do the same thing for the other equation for magnetic field intensity, we can also replace the curve of H with using the vector identity shown in the previous slides. So the left hand side is the Laplacian of H minus gamma to the square of H, that's the second order time derivative of H, equals to the source on the right hand side. So the source for magnetic field includes spatial variation of electrical current, the time variation of magnetic current, and spatial variation of magnetic charge. Spatial variation of magnetic charge. So here we use the fourth Maxwell equation, that is the divergence of B equals to the magnetic charge density at that point. Okay, so here in these two equations you can see the source and its consequence. the variation in electrical current and magnetic current, electrical charge, magnetic charge in time domain and spatial domain will result in time domain and spatial domain variation of electrical field intensity and magnetic field intensity E and H. Alright, so that's kind of the conclusion of our derivation. So in this slide, it summarizes the result. So the first equation tells you the sources for the E field include spatial variation in magnetic current M, time variation in electrical current J, and in homogeneous distribution in electrical charges. Similarly, the sources for magnetic field H include the spatial variation in electrical current J, time variation in magnetic current M, and in homogeneous distribution in magnetic charge rho and V. Okay. Alright, so let's take a look at the two equations for a spatial case, that is a source-free homogeneous medium. Source-free homogeneous medium. In the previous slide, in these two equations, you see that the E field and H field are related to spatial and time domain variation in electrical charge, magnetic charge, electrical current, magnetic current. How about what happens if at a certain point in the space that there is no electrical charge, no magnetic charge, no electrical current, nor magnetic current? Then the equation, the right-hand side of the equation become 0. Remember, this is the equations appear in differential form, which means they are valid at a certain point. 这边强调一下因为它是微分形式的，所以这里头的电场啦、电流啦、磁流啊、电荷密度指的都是在同一个点、同一个位置上面的电场、磁场、电流、磁流、电荷密度等等。所以假如你是一个所谓的 source-free region， 就是说那个空间中的那个位置是没有电荷、没有电流、没有电场，没有电荷、没有电流、没有磁荷、磁流的话，那它的等号右边就是0。那这种状况我们称之为 source-free region。但是你假如 source-free 的话，你的电场、磁场也会变0吗？不一定哦，因为你前面的关系是电场的二次边微分跟电场的二次时间边微分，二次的空间边微分跟二次的时间边微分。假如他们能够遵循某种特定的形式的话，他们的偏微分结果会0，但是他们本身不会0。那这个所谓的特定的形式，其实就是所谓的波动方程式。所以波动方程式可以把电磁能量往远处传播，即便它会经过所谓的 source-free region。So again,on the right-hand side, we have the sources, and because this is the equation appears in the differential form, so they are valid point by point. Okay, so if you comes into a region with no magnetic current source, no electrical current source, no magnetic charge source, electrical charge source, then the right-hand side equals to 0. However, the left-hand side, well, you know the left-hand side is 0 as well, but that does not imply that the E field and H field must be 0, okay, in source-free region. Even though the two equations are true, doesn't mean the electrical field intensity and magnetic field intensity must go to 0. Not necessarily. As long as the electrical field intensity and magnetic field intensity comply with certain form, then they can be non-zero. That's the reason why electromagnetic wave can propagate through space. through source-free region. The wave will continue. So, for field variations that comply with this format, which is referred as the Helmholtz equation here, and the most general name for this kind of equation is the so-called wave equation. So, as long as your field variation can comply with the wave equation, which means the solution appears in certain form 它的解是呈现特定的形式的话 ，well， 即便在没有 source 的地方，它还是能够继续的传播下去So as long as the solution of E and H field can comply with the so-called wave equation solution, they can continuously propagation within source-free regions. All right. Here we like to introduce the solution for wave equation in rectangular coordinate, in Cartesian coordinate. So let's take a look at the field representation in Cartesian coordinate, in rectangular coordinate. So the vector E can be divided into three parts. Its projection in the x-axis, and y-axis, and z-axis. Okay, so taking the Laplacian of this like this, end up with this. The wave equation appears in this form. The Laplacian of the vector E can be divided into three scalar Laplacians. Okay, so this is the scalar Laplacian. So as you can see here, the coordinate can be taken out directly, but this is only true for rectangular coordinate. It's not true for cylindrical coordinate and spherical coordinate, so be careful about that. But fortunately for Cartesian coordinate system, the coordinate, the x, y, z axis can be proved out directly like this. So by taking out of the coordinates, the wave equation appear in this form, and you can group result of the same direction together. So here is the x direction result, y direction result, and z direction result. So a good thing about rectangular coordinate is the three axes are decoupled. They are decoupled. So you can separate the Laplacian of the vector into three Laplacian of scalars. This is very convenient when it comes to Laplacian. If you take a look at the Laplacian of vector in cylindrical coordinate and spherical coordinate, it looks kind of scary. All right. So the Helmholtz equation, fortunately, in rectangular coordinate system can be separated into three one-dimensional scalar Laplacian. So the complicated function in three-dimensional space can become the product of three one-dimensional functions. Okay. So here is the three-dimensional function. Okay, the function is phi, and we know it appears in the form of wave equation, where the propagation gamma appears in the form of a complex number as alpha plus gamma. Gamma equals to alpha plus j beta. Let's begin with the lossless case, which makes your life a little bit easier. So for the lossless case, gamma can be replaced with j beta. So the square of j beta is, so here you have plus beta to the square times phi. And beta, which is the phase constant, is product of the angular frequency times the square root of mu prime times epsilon prime. And because of separation of variables in rectangular coordinate system, we can do separation of variables. So the function phi, the three-dimensional function phi, as you can see here, you have in the parentheses, you have the r vector. Fortunately, it can be separated into fx, gy, and hz. Okay? It can be separated as fx, gy, and hg. You have three scalar Laplacian. Right? So as long as you can find a solution, you can find a solution independently. You can find a such solution in the x-axis, in the y-axis, and the z-axis, and then you perform the product of the three solutions. You end up with the total solution of your waves. 所以我们接下来要把电磁场的变动沿着不同轴向观察，并找出它的解。好。So the product of the three one-dimensional function in Helmholtz equation can be dealt with separately. I mean, they can take in their Laplacian operation by itself. So the wave equation, the Helmholtz equation of the three-dimensional equation phi can be separated as f double prime. That means you have performed second-order spatial derivative in the Laplacian form in the x-axis plus fg double prime h, that is the second-order derivative in y-axis, and fgh double prime, that is the result of Laplacian operation in the z-axis, equals to gamma to the square times f times g times h. Alright? And if you divide both sides with fgh, you end up with this. Because gamma to the square is a constant, the first three terms are constant as well. So here we can define the wave equation separately. We can define the one-dimensional wave equation separately. So the constant in the axis, y-axis, and z-axis are represented with gamma x, that is the projection of the propagation constant gamma on the x-axis. So f double prime over f equals to gamma x to the square, and the same thing for gamma y and gamma z. And the summation of the gamma x to the square, gamma y to the square, and gamma z to the square should equal to gamma to the square. Okay, so finally, let's provide the solution. Alright? So here I will give you the solution for one-dimensional wave equation. For one-dimensional equation goes from minus infinity to plus infinity, the solution shall appears in these two forms. 对于一维的波动方程式来讲，假如你的环境是从负无限大到正无限大，也就是像在直角坐标里头这种线性的这种变动的话，那它的解有两种，也就是我们这边所写出来的。一种解叫做行进波 traveling wave， 另外一种解叫做驻波 standing wave。那两种解的形式不一样，不过注意哦，这个指的是类似一维的无限延伸的讯号传播的环境才是这样子的解在后面我们会看到驻坐标系统、球坐标系统，在不同的轴向的时候，它的一般解形式不是长这个样子的Alright, so this is the general solution for one-dimensional wave equation. So if the spatial domain extends from minus infinity to positive infinity, then there are two solutions. One is referred as the traveling wave solution, and the other is the standing wave solution. What kind of solution is applicable? 哪一种解释才是对的? Well, it depends on your propagation environment. Okay, so in general, if you have an unbounded propagation region, then most likely the traveling wave applies. The traveling wave solution applies. On the other hand, if your waves appears in a bounded region, okay, you have metal wires on one side or two sides, then you may end up with a standing wave. Okay, but again, it depends. 所以假如你是在没有边界的范围里头的话，那大概会是新进波的形式的解的形式。那假如说你是两边有金属遮蔽，两边有金属障碍的话，或者是一边有金属障碍的话，也有可能啦。那也就是根据你的边界条件，那有的时候它可能会出现的是驻波 standing wave 的解。All right, so let's take a look at the solution for traveling wave. For traveling wave, you have two terms: A exponential minus gamma x plus B exponential gamma x. Okay, so gamma x is the projection of propagation constant gamma in the x direction. And you can see there are function of x in the exponential form. And minus gamma x, so the first term, exponential minus gamma x stands for the wave components that is going to the positive x direction. Okay. Yeah, I guess it's not gamma x direction, it's x direction, positive x direction. And the second term goes to the negative x direction. Okay. And A1, B1 are just constants for the two components. Okay, so if A or B goes to 0, that means you have only one component. The wave only goes from left to right or right to left. And on the other hand, for standing wave, the solution appears in the hypercosine or hypersine functions. Okay, so as you can see, it's the summation of hypersine and hypercosine functions. So again, the first term, the hypercosine term, stands for the wave goes to the positive x direction, and the hypersine function, the second component, stands for the wave goes to the minus x direction. Standing waves means the energy of the electromagnetic wave is bouncing back and forth between two ends. 就是你能量没有办法继续的传下去，它是在一个区域里头来回震荡，这是 standing wave 的结果。So therefore, because the standing wave means the energy, electromagnetic energy, is bouncing back and forth within a certain region, so it's most likely the solution with a bounded region. I mean, you have metal plates, metal ends at the termination of the. Again, this is the one-dimensional problem. Okay, but fortunately for electromagnetic wave propagates in space that is defined in terms of rectangular coordinate system, the solution can be found by finding its solution in the x-axis, y-axis, and z-axis, and you do the product of the three solutions, you end up with the general solution. You end up with the solution of the three-dimensional of the wave in three-dimensional space. Okay, so this is the general solution, 一般解。Okay, 那怎么找到特定解？ To find the specific solution, you need to apply the boundary condition. So this is for the specific solution, it varies case by case. You need to find out the boundary condition given in a particular problem, so that you can find the find a specific solution. Okay, otherwise you only have the general solution. So here we kind of summarize the wave equation solution. So this is the summary of what we have done in the previous slides. So here we begins with three-dimensional equation. Fortunately, in rectangular coordinate system, it can be separated into three one-dimensional wave equations. So the solution for this three-dimensional wave equation can be found as the product of solution three one-dimensional wave equation solutions. So we can substitute the second-order derivative in space, the relationship between second-order derivative in space and second-order derivative in time. So here, this is the second-order derivative in space. This is the second-order derivative in time. You have three equations, three one-dimensional wave equations. Note that this is in the source-free regions. So you end up with only the general solution. To find a specific solution, you need to apply the boundary condition, which is usually the source condition. Okay, so you need to know how the electrical current, magnetic current, or electrical charge variate in space and time, so that you can find the specific solution. 好，所以各位注意哦，我们现在解的 Helmholtz equation 是 source-free region 的，好，也就是说它已经在外面传播了。已经离开它的 source region， 好，所以我们只能找到所谓的 general solution 一般解形式。你要找到特定解的话，你还是要回到 source region， 或者它遇到所谓的边界，哈 ，source 也算 source condition 也是边界条件的一种啦，哈。那你要带入边界条件，你才能够得到它的特定解，哈 ，specific solution。Alright, so you have three one-dimensional equations, and the propagation constant can be found as the summation of its projection on x, y, and z axis. Okay, so this is the relationship of the projections. So the solution, again, because the propagation constant is a complex number, you have the real part and imaginary part. Imaginary part stands for phase variation, while the real part stands for attenuation. So a more explicit or more convenient representation for the solution in S, Y, and Z domain can be written as this. This is the general solution. But the exponential part is separated with a real part and the imaginary part in its propagation constant. So let's take a look at this. The first stands for the wave going to the positive x direction. And because, okay, I forgot to mention that for the propagation constant, both alpha and beta are positive real numbers. Gamma itself is a complex number, but gamma, the complex number, falls on the first quadrant of the complex plane, which means alpha a positive real number, beta is in general a positive real number. Okay, so because propagation constant is a positive real number, so exponential minus alpha xx will goes to 0 as x goes to infinity. Similarly, for the b component, because the attenuation part appears in the form of exponential alpha xx, so as x goes to minus infinity, the exponential of alpha xx goes to 0 as well. So that's reasonable. That's reasonable for propagation in a lossy material. Okay, so the field attenuates as the x goes up, and the variation of the field follows a sinusoidal pattern. Okay, So this is the Phasor form. If we try to write up the instantaneous form of the solution, of the one-dimensional solution, you can times your solution with exponential j omega t and take the real part of that. You end up with this exponential minus alpha xx times cosine omega t minus beta xx. So field attenuation appears in this part, and the second part only stands for phase variation. So for the second part, the sinusoidal variation, you can as the time change, you see the dependence of time and space. I mean, this is omega t minus beta x, omega t minus beta x. So you can observe, look into the variation in t and x. So supposing that the variant of the cosine function is a constant, which means if you take in the time derivative of the variant and have it as 0, you can find out the velocity of the wave. Okay, so here you end up with omega minus beta x dx over dt, and dx over dt by definition is the velocity on the x direction. It equals to omega divided by beta x. So this is the phase velocity along the x direction. So if alpha goes to 0, then the sinusoidal function will varies as the figure shown. Okay, so if you move along with the wave at the descent speed of its propagation, you will see a constant point moving along the x direction or z direction. Okay, all right.